Alright guys, continuing on with our three-phase transformer test review. So number 33, now we're into the additive and subtractive polarities when we do the buck boost test. So for this guy, we're going to take a look at each of these transformers. In this case, we've created an auto transformer by having a jumper between H1 and X2, and we just need to see whether it provides us with the additive voltage or the subtractive voltage. So what I'm going to do is I'm going to put a dot here to denote that H1 and a dot here for X1 to denote that their polarity is the same. And I've just been doing arrows to show my instantaneous magnetic polarity. So I'm going from 1 to 2, and over here I'm going from 1 to 2 to show my magnetic polarity. And then you can see that it's not closed, right? So we haven't closed this auto transformer whatsoever, otherwise we'd create a bomb. We have 120 volts as the source. That's being placed to H1 and H2. We've got a jumper over here to take this isolation transformer and create an auto transformer, and we're seeing how these magnetic fields either add or subtract. So I'm going to start here at this point right here where my meter lead is, and I'm going through this coil right here. It looks like I'm going with the arrow, and I'm going over up to this jumper here, and I'm going with the arrow as well. So this voltage right here and this voltage right here are going to sum together. So this guy right here is going to see the 120 volts that I'm seeing on my first winding plus the 24 volts that I'm seeing on the second winding. So the meter is going to read 144 volts. So that guy was our additive connection. Okay, if that one's the additive, then most likely the next one's going to be the subtractive. Let's take a look, guys. So for 34, again, I'm going to do this. I'm going to put an arrow, a dot here for my H1, a dot here for my X1, denoting my instantaneous polarity. I'm putting an arrow showing my magnetic polarity going from my 1s to my 2s. And again, I'm going to start here. And I'm going to go through this auto transformer. It's a distribution or isolation transformer that we've now created into an auto transformer by putting this jumper between the secondary and the primary. And going through this winding, it looks like I'm going against the arrow here. And then over here, I'm going with the arrow. So those two magnetic fields are going in opposite directions. So I'm going to have my 208 volts minus my 120 volts, and the difference between those guys is going to give me 88 volts. So this meter right here is going to read 88 volts, and this is our subtractive. Okay, again, sorry, can't spell today. Again, when we were doing that buck boost test, we didn't close the transformer. These two connections right here and right here are open for us to measure with our voltmeter. If we close this, then we've created a low impedance path with this 208 volt source, and we're most likely going to blow the fuse, or we're going to smoke these windings if we closed it. There is no current flowing though. It's strictly a pressure that's being developed. Right here and right here are open, and we're looking at that resulting voltage. And in this case, it's the subtractive voltage of 88 volts. Whereas for 33, again, at this point and this point, we're still open. There is no current flowing. We're just looking at the resulting voltage. These two magnetic fields are going in the same direction, and we had the additive voltage, or 144 volts. All right, let's keep going. Let's go to 35 here, guys. Now this one here, it didn't print out very well. It's a little bit fuzzy. So wherever I grab this from, the impedance here is equal to 6 ohms. Okay, so you can pause the video here. Line voltage on the primary is 13.8, line voltage on the secondary is 480, and the impedance of each of these resistors is 6 ohms. It's a balanced load. So you pause it here, find all your values, start the video back up, and I'll walk you through how to find each of these values. Okay, so let's start off with our line voltage here of 13.8. So here on the outside we have 13,800 800 volts as our line value. And then on the secondary, we've been given 480 volts as our line voltage. Okay, knowing that that's our line voltage, that tells us that that 480 volts is brought across, so that'll be our line voltage to this point and this point on the delta. And we know that on the delta that the phase voltage is identical, so this guy is also 480 volts on, sorry, different chart that I'm used to, 480 volts on the phase. So let's just look at these guys. We'll just quickly drop in our rules. V line equals V phase, I line equals I phase times √3, identical to the first test that we had. Here we have, for any of our y's, we have I line is equal to I phase and V line is equal to V phase times √3. Okay, so let's work with those equations and the given values now. So let's see, we can find, what are we going to find first? We found 480 volts there, right? And that 480 volts is going to go across each of these resistors. And we just found that that was our phase voltage there, right here. And the next step is to find our phase current, right? So this was step number 1. Step number 2 is to find our phase current. And at that point, we have 480 volts impressed across 6 ohms of resistance. And when we take 480 divided by 6, that gives us a disgusting 80 amps flowing in that circuit. So our phase current here is 80 amps. And that current is going to be right there on the inside of that delta. Okay, once we found that phase current of 80 amps, then we can find the line current. This one didn't print out well, but this is connected in here. And we can now find the line current by taking our 80 amps on the phase. We're going to multiply that by √3, and that's going to give us a current of 138.56 amps on the line. So our third step here was to find our line current, 138.56 amps on the line. Beautiful. So now we got everything for our load here. So we have our delta load, and let's move back to our Y resistive source. So we have our 480 volts on the line, which we have here. That was our given. And then we know, we've already memorized these values, that our phase voltage is going to be 277 volts on the phase. So in an effort to try and save time, guys, I'm not going through everything on the calculator here because we should know these values now. So this value right here is 277 volts on the phase. And let's see, we're just going to follow that current back, right? So we had 138.56 amps on the line. Well, that is the same over here. We got 138.56 amps again on the line, because if we follow that current back, it'll be identical. And then based off of this rule, I line equals I phase, well, that same current is going to be here on the phase, right? It's more like a series circuit there. So 138.56 amps on the phase. So we'll drop that in here. Beautiful. So this was our fourth step, finding our 277. Then we did our fifth step, taking our line current across, and then we used the fact that the line and the phase currents were identical to find our phase current on the Y secondary. Excellent. Now we need to find the ratio. So the ratio here is based on the phase, but we don't have our phase voltage here, but we can easily find that. On the Y, we're going to take our 13.8 and then divide it by √3 in order to find our phase voltage. And when you take 13.8 divided by √3, you get 7,967.43. 7,967.43, and that's our voltage on the phase on our Y primary. And now we can find the ratio. That was number 6 for steps. So the ratio now is 7,967.43 divided by 277. Okay, so our ratio here is based off the phase. So we're going to take 7,967.43. That was on our primary. And then we've got 277 volts on our secondary. And again, we're going off of our phase values because that's where the transfer of energy is, right? From here to here. Okay, so when you take those values, then your ratio ends up being 28.76 to 1. Okay, so now we've got our ratio, and now we can find our primary phase current. So here we've got a higher voltage. Here we've got a lower voltage. That means that this current is going to be higher, and this current is going to be lower. It's going to be lower by a factor of 28.76. So in order to find our phase current on the primary, we're going to take our secondary current of 138.56 amps that we have on the secondary, and we're going to divide it by our ratio of 28, cruise control here, 28.76, and that gives us a phase current on the primary of 4.82 amps. Beautiful. Now, some of you are saying, why didn't you use the line? I could have used the line because it's the same ratio. This is a mirror image, right? But I'm trying to keep you guys on the same track using your phase voltages for the ratio there. Okay? Using that ratio, we then found our phase currents. And we know that if there is 4.82 amps on the phase, then there's clearly one path for that current to flow. And on the outside, we're also going to have 4.82 amps on the line. Beautiful. And that gives us everything that we need, guys. If you want to do a check, then you can use your line voltage times your line current times √3. So your VA in the primary should be equal to your line voltage times your line current times √3 on the secondary. So as a check, you can also look to see that your VA in is equal to your VA out. Excellent. Okay, let's move over to question 36, guys. You can pause now to double check all your values. So 36, guys. Now this one here again is a little bit fuzzy here. This value right here is 1.5 ohms. So each of these resistors has a resistance of 1.5 ohms. Again, it is a balanced circuit. This one got cut off here. Okay, so you can pause here and walk through and find all your values. Okay, so let's start by putting in our values that we've been given here with the 2.8 and the 240 volts. So line voltage on the primary here is 208 volts, so we'll drop that in here. And we've been given a line voltage of 240 volts on the secondary. Beautiful. Okay, let's take that voltage across and we'll start over here at our Y resistive load. So our 240 goes across, and we also have 240 volts on the line here, right? So from this point right here to this point right here, there's 240 volts. And then on our phase, it's going to be √3 less. So where am I going to draw that? I'm just going to draw that up here, guys. So the voltage on the phase here is going to be 240 volts divided by √3, right? Because our voltage is lower by a factor of √3. And I found 138.56. That's our phase voltage there. Okay? So now that we found that guy, let's drop that in here, 138.56. That's our phase value, step 1. Step 2, next step is to take a 3-phase circuit and break it down into a single phase Ohm's law equation. So we're going to find our phase current here for step number 3. In order to do that and find that current that's right there, we're taking the 138.56 volts on the phase. We're impressing that against 1.5 ohms. And when you take 138.56 and divide it by 1.5, then it gives you a phase current of 92.37 amps. Okay, so that's this value right here, 92.37 amps on the phase. Okay, and then we can see that on the Y that our line current is going to be identical. So this is going to be 92.37 amps on the line. Excellent. Okay, taking that value back, we can clearly see that the same current would be here on the line. So here on the outside of this delta, we have 92.37 amps on the line. So that's this guy here. We've transferred this over. But the current on the inside of the delta is going to be √3 lower. So our value on the inside here of our delta is going to be 92.37 amps. We're looking for a lower current, so we're going to divide by √3. And when you take 92.37 divided by √3, you get 53.33 amps. And that's our phase value for this delta. Right here, 53.33 amps. And that was our phase current. And then for the delta, we know that our line voltage and phase voltage are identical. So this guy is also going to be 240 volts on the phase. Beautiful. Okay, next thing we need to do is we need to find the ratio. Now remember that the ratio is on the phase. The transfer of energy is from here to here. So we're not going to use the line values, right? Don't get tripped up using the line values, especially when we have different animals being a Y and a delta primary and secondary. We need to look at the phase values. We know that the voltage here on the phase is 240 volts, but we don't have our phase voltage here yet. But if we have 208 volts from here to here on a Y, then we know that the line to neutral voltage is going to be 120 volts on the phase. It's always √3 less on the Y. So that gives us a phase voltage of 120 volts on the phase. And the ratio is based off of that phase value because that's where the number of turns are. And so here we can see that we've got 120 divided by 240, right? So that gives us a half. Or we can do the 240 divided by the 120, and that gives us 2 for our ratio. I would much rather use 2 rather than a fraction here. So the ratio here is 1 to 2. There's 2 times as much or twice as much voltage on the secondary. So the ratio is going to be 1 to 2. You could also say that the ratio is 0.5 to 1. I just don't like doing that. I like using round numbers here. So I'm going to use my ratio of 1 to 2 here. Again, I have a lower voltage here, a higher voltage here, so be careful, don't get tripped up. This is a step-up transformer. On the secondary, the current is going to be lower, and on the primary, the current is going to be higher so that my VA values are identical. So it's going to be higher by a factor of 2. So I've got 53.33 amps here, and my phase current here is going to be double that value. And when you take 53.33 and double that, you get 106.66 amps on the phase. Okay, so we used our phase ratio here on the voltage to find our phase currents here. And now that we found that this current here on the inside of the Y is 106.66 amps, then we know on the outside the current is identical, 106.66 amps on the line. Beautiful. this was our step 5. I kind of lost track there, so this is step 6. We made sure that we found the voltage for step 7. Then we used our phase voltage over here for step 8. Step 9 was our ratio. Step 10 was our phase current. And then finally step 11 was our final line current. Alright guys, you can pause the video here and double check all your values. And for this video, I'm going to keep going with questions 37 and 38. So let's go on to question 37. So same recipe here, guys. The impedance here, again, a little bit fuzzy from when I photocopied this. This is 3 ohms. So each of these resistors are 3 ohms. Again, it's a balanced load. And we've been given the fact that our line voltage is 7200 on the primary and 208 volts on the secondary for our line voltage. So let's draw those guys in. Okay, so our given voltages here are 7200 on the line. And then over here on our line voltage on the secondary, we have 208 volts on the line. Okay, we'll use those values now to find all of our other values. So we have 208 from here to here. So that is evident that that voltage is going to be on the outside as well, right? So from here to here, our voltage is going to be 208 volts on the line on our Y resistive load. So where's that? Right here. Okay, again, we can put our rules in here that we know that I line is equal to I phase and V line is equal to V phase times root 3. And do we have any deltas? There, delta over here, we're going to say that our line voltage and phase voltage are identical, but the line current is greater than the phase current by root 3. Okay, so we have 208 volts. We know that this voltage is 120 volts on the phase. Okay, again, it's root 3 less. So right here, our phase voltage is 120 volts. And now we're going to take a 3-phase circuit and we're going to break it down into a single-phase Ohm's law equation. In this case, we have 120 volts being, sorry guys, sometimes my finger hits the side there. Okay, so 120 volts, and we're impressing that across, what, 3 ohms there? So we have 3 ohms of resistance, so 120 divided by 3, and that gives us a phase current of 40 amps. Okay, so that gives us this value right here. That's our phase value. Okay, and let's see, we can just draw that in. We know that this current on the inside is now 40 amps on the phase. We can clearly see that that current is identical on the line, and if we follow that back, then we have 40 amps on the line as well. Okay, so we have, for step 4, identical line current. That value is here as well. And if we keep following that through, then that value is also here on the phase, right? So we have a Y feeding a Y. So our phase current here is going to be 40 amps on the phase as well. Okay, these are mirror images of each other, so we know that this voltage right here is 120 volts on the phase. And now we've found everything for the secondary there. And let's see, we can now find the ratio. We just have to drop in our phase voltage here on the delta. It's identical, right? So we have 7200 volts on the phase. And we know that our ratio right here is based off of our phase values. So in order to find our ratio here, we're going to take 7200 and divide it by 120. And that gives us a ratio of 60 to 1. So this value right here is 60 times greater than our secondary, so we've got a ratio of 60 to 1. And to help ourselves out, we can see that this is a higher voltage, this is a lower voltage. That means that this current is going to be higher, and this current is going to be lower. This current on the phase is going to be lower by the same ratio, by a factor of 60. So our phase current on the primary is going to be equal to our 40 amps that we have on the secondary, divided by our ratio of 60. And that gives us a phase current of 0.67 amps. So that's a phase value. So again, we're just going to drop that value in here. We're going to put that right here. 0.67 amps on the phase. But on the outside, that value is going to be √3 higher. So we're going to take the 0.67 that we have on the phase. We're going to multiply that by √3. And our line current ends up being 1.16 amps. Beautiful. Okay, so on the secondary, we have 40 amps flowing on the secondary, but in order to get that 40 amps to transfer from the primary only needs 1.16 amps on the line. The reason why it only needs that little amount of current is because the disgusting voltage of 7200 volts on the line. Again, if you wanted to double check this, you're going to take your VA in equal your VA out, and double check that your line voltage times line current times √3 is equal to your line voltage times line current times √3. Okay, let's finish off 38, guys, and then we'll take a break. So let's see, 38, what have we got? We've got an impedance of 4 ohms now. So right here we've got our impedance is equal to 4 ohms. So you can pause here. I've given you 4,160 volts for the line voltage, a random 440 volts here for the line voltage on the secondary. So let's just draw those guys in, and then you can pause and figure out all your values. So we have 4160 volts on the line. Then over here, our line voltage on the secondary is 440 volts on the line. So pause here for 2 seconds, work through the values, and then start back up, and I'll walk you through all the answers here. Okay, so we have a delta feeding a delta, right? So we have delta primary, delta secondary, and then we have a Y load right here. So our rules for the Y are that I line is equal to I phase, and V line is equal to V phase times √3. And over here for the delta, we have V line is equal to V phase, and I line is greater than our I phase by a factor of √3. So our first step is to take this 440 volts that we have on the line and bring it across here, and we can see that the voltage from here to here is the same as from here to here. So our line voltage here is 440 volts on the line. That was step 1. Step 2 is we need to find this phase voltage right here. So our phase voltage right here is going to be √3 less. So we'll take our 440 volts that we have on the line. We're going to divide by √3. And that gives you a random voltage of, what do we got? 254 volts on the phase. Okay, so this guy here is 254 volts on the phase. That was our second step. Third step is we're going to take a 3-phase circuit here and break it down into a single-phase Ohm's law chart. So we have 254 volts impressed across 4 ohms. So let's just do our Ohm's law. 254 volts on the phase impressed across 4 ohms on the phase. And when we take our 254 divided by 4, that gives us 63.5 amps on the phase. So this guy right here was our third step, 63.5 amps on the phase. And again, if we have 63.5 amps on the phase, then we're also going to have 63.5 amps on the line, because those guys are identical. Beautiful. That current comes from here, so we also have 63.5 amps on the line here on our secondary. That was step number 5. Okay, our phase current on the delta is going to be less, right? Because our phase current is √3 less. So for this guy right here, we're going to take our 63.5, we'll divide it by √3, and that gives us 36.66 amps. That's our phase value. So the current that's on the inside of the delta is 63.5 divided by √3, which gives us 36.66 amps on the phase. Okay, our voltage here is identical, so we have 440 volts on the line, meaning that we have 440 volts on the phase. So this voltage right here is also 440 volts. And now we found everything for our secondary, and now we need to find our ratio. Now our ratio is going to be identical to the line ratio, because our line voltage and phase voltage are identical as well. So for our ratio here, we have 4160 on the primary, we have 440 volts on the secondary, and the ratio ends up being 9.45 to 1. So we'll put that here. That was step 8. And we're going to use that ratio in order to find our phase voltage here. So let's see, we have a higher voltage, lower voltage, and we've got, actually we're not going to find our phase voltage. We already know that. Donkey. Right? That's identical. We're going to use that to find our phase current. So we have a higher voltage, lower voltage. That means that on the secondary we're going to have a higher current. On the primary we're going to have a lower current by a factor of 9.45. So our phase current here is going to be our secondary current of 36.66 amps. On the secondary, we're going to divide by our ratio of 9.45. And our phase current on the primary is equal to 36.66 divided by 9.45, and I found 3.88 amps. Okay, that's our phase value, and again we can just draw that value in maybe right here. Okay, but we have 3.88 amps here, 3.88 amps here, and 3.88 amps here. Our final line current right here is going to be equal to our 3.88 that we have on the phase times √3, and final value is 6.72 for the line current on the primary. Okay, last step again you can do here is you can check that your VA, which is equal to your V line times I line times √3, is equal to your VA on the secondary, which again is equal to your V line times I line times √3. So you can always use your VA values as a check there. Alright guys, that was a lot of calculations. Let's take a break for a bit. You can come back in the next video in the playlist and we'll keep going with question 39.